Okay, so it's unusually quiet today. There's going to be presentations at 4 p.m., right? Yeah, planning on that. I received both groups' deliverables. I appreciate that, and I'm looking forward to seeing the presentations and getting some feedback to you. So today's class is going to build on the material that we've covered the past 2 lectures. But it's going to bring in a bunch of additional considerations when it comes to subclassing. So who could remind me what we talked about during the last 2 lectures, during the lectures last week? What was the focus of the discussion on? Yeah. Yeah, LSP, Liskov Substitution Principle. And broadly, what does Liskov Substitution Principle have to deal with? What's its kind of focus? What is it talking about? Yeah.
Subclass needs to provide it needs to satisfy all the predicates of the superclass.
Good. Yeah. So I'll refine that a little bit, but a subtype, something we can pass around as if it were an instance of a supertype. Say, an instance of a class that we can pass around as if it's a collection, as if it's an iterable, as if it's a set. That it has to adhere to all the properties of a collection, an iterable, a set, etc. Right? It has to make the same guarantees. And why is that? Why is that needed for safe operation? Why did I argue that was needed for safe operation? Anyone?
Well, I guess type, like, because a subtype can be passed around as though it is the other type.
Good.
Someone can use it assuming that it's going to do the things that the supertype does.
Yeah, exactly. So, hey, if it can masquerade as if it can be treated as a collection, an iterable, a set, a what have you, it means that the person using it, all they know is that, well, this is a collection, this is an iterable, this is a set. And so they're going to treat it as such. And they're going to potentially be really counting on when they write their code. And they're writing the code that uses that instance. They're going to be counting on the things that you can count on for a collection, an iterable, a set, or what have you, whatever the super type is. Now, if it's secretly your class, that's all fine and good as long as it adheres to those promises, as long as it makes those same guarantees. But if your class deviates from those guarantees, it can be really thrown off. And mind you that the code that may be using an instance of your class may have been written long before your class existed. It may have been written by someone who has no idea that your class will ever exist, who has no particular interest in your class. And you're using their code. And you can't simply say, well, your code, my class is different. It's a collection, but it doesn't adhere to all the promises collection. That doesn't cut it. They're not going to go out and want to futz with their code just because now you've introduced a class that's sort of a collection and sort of not in terms of what it does. So Liskov substitution principle is all about subtypes, things that be passed around as if they're an instance of a supertype, remaining consistent, remaining true to, remaining guaranteeing the promises that are guaranteed to the supertype. Because someone using the instance of that subtype, they might be using inadvertently the instance of subtype. They don't know what it is. All they know is if it's a supertype. All they know is it's a collection. And their code could be counting on all the normal properties that you can establish about a collection from its documentation. So if you're going to be passing around your class as if it's one of those, it's incumbent upon you to adhere to those promises. But ladies and gentlemen, well, okay. This is broadcast to the world, so there are most emphatically pretty late. Ladies and gentlemen, today's lecture is going to go long beyond the issue of promises. It's going to go far beyond this issue of needing to adhere to the guarantees. Today's lecture, ladies and gentlemen, is going to be about implementation issues. And it's going to be about not just subtyping, not just being able to pass it around as if it's an instance of that supertype. It's going to be about subclassing, which gets into issues of implementation, inheritance. Okay, so ladies and gentlemen, you can tell me, what happens when we declare A to be a subclass of B? A subclass, say, extends B. And B is another class, and our class that we're creating extends it. What benefits do you get from that? Okay, good. Good. So you inherit all the properties of the superclass. So I'll separate that into two things because I think it really needs to be teased out in two ways. So one thing is that you create a subtype for the superclass. So you can pass it around as if it's, so if A is the subclass of B, you can pass around an instance of A as if it's an instance of B, right? You can pass it around like that. It's not the only way to create a subtype. You can create a subtype by implementing an interface and being able to pass around as if it's any implementation of that interface. But with subclassing, you get a subtype. You can pass it around as if it's an instance of the superclass. But secondly, you inherit the implementation. You get all the fields of the superclass. The superclass is an int field called count. You now have an int field called count. If the superclass has a method called add that's defined in the superclass, unless you override it, you get that full implementation of that method, right? You get to use that code. Not just like saying you implement an interface and you're responsible for defining methods for each of those things in the interface. You actually get all the code of that superclass. You get all the fields of the superclass, all the data structures of the superclass, all the implementation details of the superclass. You get all of them for free. That sounds like a pretty good deal, right? You get all of that, and then you can build the top of it. Are people comfortable with that idea? If A subclass is B, if B as the superclass, implement submethod foo. A as the subclass now gets a foo of its own. And it could override it. It could say, well, I don't want that foo from the superclass. I want to have this other one. But if it doesn't, it gets it for free. Do people appreciate that? You understand that? Yeah, okay, good. This is like 270, 101. That sounds weird. This is fairly basic 270 stuff, right? So I hope you're feeling pretty good about this, right? Now, one of the consequences, though, the consequences of this are very significant. The fact that we inherit the implementation. We don't just have to adhere to the promises. It's not merely as if we're implementing an interface and we have to be able to be passed around as if it's one of those. Now we've actually got the goodies, the implementation goodies of the superclass. The details of how it works. Not just what it promises, not just the guarantees that we have to adhere to, but actually we get tied up in all of how it works. Okay, so let's go through a little thing here. So we have so we have, forgive the flipping of A and B. We have a superclass A and a subclass B that extends A. A defines two methods, foo and bar. And B, the subclass of A, overrides bar. People comfortable with that? So it overrides it? Some languages allow you to say explicitly overrides. Some, you have an annotation with an ampersand that you can use to indicate it. And I don't want to get into it, but fundamentally it overrides it, okay? And then we have a class, another class, a client class that actually uses a B. It uses one of these guys down here to the right. Now, I'm providing the example because students in some previous versions of 371 have sometimes, it's like they've never revisited, really let the issue sink in of this, and it's going to be critical to this lecture. So I really want to go over this issue, make sure we're rock solid with it. So this client class on the left, it's some code that uses a B. Yeah? See that? It creates a B. Do you see that? Okay? And now it calls foo on B, on that instance of B. Okay, ladies and gentlemen, what happens here if, when we call foo? What bar is ultimately called when we call foo over here on this instance of B? Which bar is it that gets called? Bearing in mind that when you call foo, eventually bar gets called. Which bar is it that gets called? Is it this one? Or is it this one? The overridden one. That's right. Because this is a B. It's actually not an A. B's override this instance of B, or so the class B overrides this bar. So if you create a B, you're using this code for A. That's why I said you inherit the code. You've got that code for A. But when it calls bar here, guess which bar it's calling? It's calling this overridden one. We're getting this code for foo for free, but it's calling our bar. Are people clear about that? Because people evince great silence here. You don't seem to be going to sleep with boredom right now. Let me actually frob this some more. Okay. Let's just test your intuition more because I need you to be really comfortable about this. Okay. So we've used foo, bar, baz. So now the next one is zap. Okay, so zap is going to take in something that we simply know as an A, okay? And I'm going to, and then it's going to call foo on that A, okay? All right? And we're going to pass it in. Here, we're going to call zap with a B, with an instance of B. But from all zap knows is that it's an instance of A. So we call foo here. Okay, so here in baz, we've created a B. We've created a new B. And we've called foo on the B. And as was correctly indicated earlier, it called this bar, right? Here. Okay, because we're dealing with the B. Now we're calling zap with B as an argument, or this instance of B here, passes it to zap. Zap treats it as if it's an A and calls foo on it. Which bar is called here? Riddle me this. Which bar is called here? Oh. The overridden one. Just because it calls it an A, secretly it's a B, and that's what really matters. In C++, we talk about v-tables, and a v-table is such that it's going to call this overridden one. But this is really important to understand about how Java works, okay, folks? This is not a small issue, and you want to be rock solid on this before you graduate, because you're going to be working with code bases that absolutely depend on it. So if you're not feeling that comfortable with it, I'd be happy to discuss in office hours. I'd be happy to answer questions right now. I'd also, could refer you to books on Java that would hopefully let you tune up this knowledge in you. Because this is absolutely rock solid importance. So you want to be rock solid on this before you go into professional development. So both of these instances over here on the left, they call foo, which is going to call the overridden bar. Why? Because we're dealing with an actual type, an instance of actual type B. Are people comfortable with that? Both of these guys, even though, so here we call foo. B has got its own version of foo, but it's calling its bar. As Wei Zhong said, it overrode bar, and so it's calling its own bar. This code here, it's calling its own bar because it's got an overridden bar. Here, we're passing in something that's secretly an instance of B as if it's an A, but it's a B. It's a B, folks. From the standpoint of Zap, it doesn't know it's a B. Maybe this code is in another class, which was written long, long, long before B existed. But when it calls foo, because this is secretly B, it's going to call off to the version of foo which is associated with class B, and it's going to call it on bar. So both of these call bar. Are people okay with that? People okay? Again, happy to talk about this in office hours, happy to go over examples. I would welcome you to try things out on your own with Java, but this is foundational, and you want to be very solid, because I'm going to be depending on this in my discussion this hour and potentially some of next lecture. Okay? Okay, so let's build on this understanding. Good? Okay, so let's talk next. Oh, okay. Well, yeah, so it's bar in both cases, folks. It's bars all the way down. Okay, so we're going to keep that in mind, okay? When a subclass overrides an instance of the superclass, overrides a method that was defined by the superclass, that method is going to be called, but potentially by other code that was defined only in the superclass. Okay, so ladies and gentlemen, we're going to keep that in mind, store that away. We're going to use it in 2 slides later. Okay, or 1 slide later. I think it's 1 slide later. Okay, ladies and gentlemen, just as a reminder from last time, here's a class, and here we're going to have a subclass. These are their interfaces here, okay? So on the left, we have an add and an add all. And on the right, we have an add and an add all implemented for the subclass, the subtype. And then we're going to have an extra thing, get add count, that's going to return the number of times things have been inserted in this set. So it's going to do all the things that are, this subtype, the subclass is going to be promising all the things that are promised for add and add all, okay? Promising the same behavior for add and add all. The only thing is it's going to be providing this extra bit of information to people who want to know it, how many things have been added into the set since it was created. Does that make sense? So it's providing that extra bit of information. The guarantees provided for add and add all are the same as for the supertype. Is this a legitimate subtype by the Liskov substitution principle? Yay or nay? Yes. Yeah. Yeah, we don't see anything really bad here. It's not like it's changing the behavior of add all. It's not changing the behavior of add. It's not suddenly having add be delete, right? It's not turning something that's read-only in the super type to be, modifiable in the subtype. Not changing something immutable to be immutable, right? So this is a perfectly legitimate subtype from the perspective of the Liskov substitution. Well, it just packs a little bit more functionality without changing the functionality of super type, right? If you were dealing with this one on the right as if it were a hash set, if all you knew about in the world were hash sets, and you had secretly had instrumented hash that, you'd be none the wiser. You get no rude surprises, right? Right? Things are hunky-dory with it from a Liskov substitution principle. Okay. Yeah, I'm going to say, now we're in the domain of subclassing. And I'm going to say that if we went to implement that subtype that we saw, we actually went to put it into practice. We went to live up to those promises, live up to those guarantees, then I'm going to be doing something risky here. Okay? So here's my attempt at implementing. And you're going to tell me why I say this is risky. I hope you'll tell me why. It's definitely risky. Okay, so here we have add, an implementation of add, and whatever the superclass's add does, we're going to call off to that, delegate to that, but we're going to also increment our add count. Because remember, we're going to need to support this method get add count. So we need to kick around a little bit more information. So we have this extra variable, extra field, extra instance variable, it's another name we use for it, called add count. And in add, we're going to do whatever the superclass's add does, but we're going to also increment add count. And in add all, when we get called in add all, we're going to do whatever the superclass does for add all, but we're going to add to our add count things that count how many things were being added in. So if we're adding in 2 things here, it'll be doing add count plus equals 2. If we're adding in 3 things here, in other words, if the collection has 3 things in it, we'll be doing add count plus equals 3. So we're going to be keeping track of the add count, and then get add count is just going to return the value of that instance variable. Does that look, first of all, at a rough level, does that look like a reasonable implementation? Why do I say that it could be a risky implementation? Yes, which one?
If the add something is not if it is not allowed to add something, instead can add can't be plus? If it becomes a false.
Oh, okay. Okay, so that's a good question. So, in other words, so I like the way you're thinking, Wayne. Great job. If the superclass's add, say, rejects this, right? Like maybe it throws an exception. Now maybe we're going to be treated as if it's added, but it's thrown an exception, and we're going to have record as if it added. So great idea. And my hat is off to you. That's a very good point. I'm not after that point here. Let's assume that I should have had it so that let's assume the preconditions for add are the same as here. So you're guaranteed to never have a precondition that causes a problem over here. Okay, but a very good point. But let's not deal with the failure case. Although I really like the way you're thinking. Good software engineering. Okay, but there's another problem that I would say this is risky. Why? What am I counting on about the superclass here, ladies and gentlemen? What am I counting on about the superclass in this implementation? What am I implicitly counting on? Anyone? I'll give you a hint. Is there any way add count could sometimes be double counted? You're adding something, you're going to add 3 things in, instead you're going to have 6 things added. The add count's going to go up by 6. Okay, although this is actually counting the number of times add count has attempted to be adds. So we'll assume that it's supposed to count those things. So good call, good call. That's not what I'm after here, though. We could define it, so that's not a problem. So even if you add the same thing multiple times, you're supposed to accumulate that. You're supposed to count that. Let's assume that we are doing that. So why else could it be double counting? Well, ladies and gentlemen, I'm going to point to this particular call here. We do add count plus equals c dot size, and that we call super dot add all. I'm going to claim that we're counting on how add all is implemented in the superclass. Something about how it's implemented. What would that thing be? Let's suppose add all in the superclass calls add. Let's suppose the implementation of add all in the superclass, the class from which we're inheriting, let's suppose that it calls add. For each element that's being added in this collection, it just loops through each item in the collection and calls add. Why could that cause problems in our implementation? Yes, Joe?
So you're adding to add counts the size of the collection and then adding to add count every single time.
Exactly. So ladies and gentlemen, suppose I were to add something in here of size 3, a collection of size 3. Here I do add count plus equals 3. Great. Then I call off to add all in the superclass. And the superclass add all calls add. Whose add is it going to call, folks? Is it going to call the add in the hash set, or is it going to call our add? Remember what we saw earlier with that example with A and B. Which one is it going to call from here? If add all calls add, which one is it going to be calling? Folks? It's going to be calling the new one. It's the same thing we basically saw with this, folks. That if we had foo here and it called bar, and we've extended it, we've subclassed it, and we've overridden bar, guess what? The code to foo that we're using here calls our bar. Folks, this guy here, super.addAll, it's going to be running along here. If it calls add, it's going to call this add. And suddenly, now for each of the items in the collection, it's looping through each item in the collection, perhaps, calling add for it. And so we've added all 3 up front to add count. And now we're going to be calling add, and it's going to add 1, 2, 3, and it's going to have added 6. Can you see that? Are people comfortable with why that could be going on? But what should make you... So that's risky. But what I'm hoping is that there's a deeper sense of concern here. A sense almost of being tremulous, of being very wary, of realizing there's real danger here. Because ladies and gentlemen, guess what? We don't know what the superclass is doing sometimes. We don't have access to its code. Again, how many of you have looked at the code implementing java.object? I don't think anyone has. So if you're subclassing some code written by someone else that you got in some jar file or whatever, now suddenly you're counting on how it's implemented. Suddenly you're counting on, well, does add all call add? Suppose add all doesn't call add. Suppose add all in the superclass loops through each item in the collection and simply adds it in directly to its data structure. It doesn't call add. Would this work? Yeah, it would. So, folks, should be a little bit disconcerting. Suddenly, whether or not our code works is tied up with how things are done internally in this superclass. Whether one thing calls a different thing or not. Something we can't observe directly in many cases. So what I'm saying is this is a risky thing. Because we don't know whether add all will call add, in which case we'll be double counting, or whether it in fact just adds things indirectly to some data structure, in which case we're not double counting. Now, suppose that you could call up your buddy who works at Oracle and says, tell me about the implementation of hash set. And they say, oh, it doesn't Add all doesn't call add. It just adds directly to the data structure. Are we in good shape now? Why not? They're going to change it. The next version round, next release of Java, they may change it so it does call add. And now we're up a creek without a paddle. Your buddy is not going to call you back and say, hey, guess what? They just changed it. He's got too many other buddies calling him up and saying, does tree map call this internal? You know, they don't have time to call up everyone who implements a subclass of this. So that presents a bit of an issue. Now our life, the correctness of our code, whether our code has a bug in it or not, is dependent on the vagaries of some code base that we don't control, where we're not going to be notified if it changes, and where we probably don't even get to know what it's doing internally directly. Even if we experiment with it, there's no guarantee it's ensured. Here's another case. Ladies and gentlemen, class on the left is a superclass, class on the right is a proposed subclass. Again, when I say class here, I mean not merely subtyping. After all, instances of the thing on the right can be passed around as instances on the thing on the left. That comes automatically with subclassing, the ability to do that. Though the question is it a little bit legitimate behavioral subtype? That's a deeper issue. But this is furthermore a subclassing. Subclassing furthermore inherits the implementation. So, for example, the implementation of these methods we inherit here. Now, two of them we've overridden. We've overridden set value, we've overridden get value. And the question is, folks, is that enough? So here on the left, we have a class, and we have a get value and a set value, and something called isPositive. And on the right, suppose that we want to modify how that value is stored or whatever. We want to change the data structure involved or what have you. So we override set value and get value, okay? Oh man, they should be capitalized in consistent ways. I don't want you to be distracted via that. Okay, so is this enough on the right-hand side for us to create a full subclass that's working of the superclass? Why not? Yeah. Okay, good. Good. So this superclass may be doing some clever stuff, for example, maintaining, like if something was recently set as for an instance of the class, it may retain a cache of it so it can return quickly whether or not that's positive in the future. And we don't, and our implementation doesn't know about that cache, and so isPositive might not work. Could anyone give me a case where isPositive would be working in our subclass? If isPositive was working, did what? If its implementation had what characteristic would our subclass work? Yeah, does it call get value? So if isPositive is simply calling get value to get the current value of the variable, the current value of this instance, then isPositive might work just fine and we don't have to override it. On the other hand, if isPositive is somehow depending on a cached version of it, it somehow depends on some direct field within this superclass, then we have to override that as well, right? To have it work properly in the subclass. So the question is this subclass correct? The answer is, it depends. It depends on this thing we typically can't observe directly, whether isValue directly calls getValue or not. And the same thing here. Is this correct? It depends. What does it depend on? This thing we can't easily observe. Whether add_all calls add, for example. Okay? Okay, so with subclassing, ladies and gentlemen, beyond subtyping, we've got some risky business going on. Subclassing implies subtyping. If you create A as a subclass of B, you can pass around an A as if it's a B. And so we have to stay true to the Liskov substitution principle. We have to adhere to that. And that was covered in the past 2 lectures. That was all about the promises we make. Are the promises made by this subtype, in other words, subclass here, consistent with the promises made by the supertype, that is superclass. Great, and we have to adhere to all of them. Basic stuff. But that's about promises. Now, we're dealing with things that have to do with the implementation. What calls what? What variables do they use? Are they using this variable, or using a cached version, or what have you? So, ladies and gentlemen, here we're dealing with how do we implement those promises? So the Liskov substitution principle is all about what promises we make. And now we got to live up to them. We got to live up to those guarantees. And we have to do it without, even if the superclass changes. We don't want our guarantees to suddenly break. If FedEx suddenly changes how they manage their plane schedule, we don't want our packages to suddenly be late. We want to have a robust system which is reliable even if things change that we can't control, like the implementation of our superclasses. Okay, so the problem here is that it can be quite easy to break superclass methods that we inherit. And we may be depending on things that can change out from under us, that can change at any notice, without notice to us, and cause our code to break on customers' desktops. This is bad news. If we're depending on the vagaries of all these people out there of different code bases, and whether they happen to change if add all calls add or not, if our code, the correctness of our code, if its ability to work properly depends on those things that are outside our control where we'll never get notification, we're in a bad way. We're in a bad shape if we're dependent on those things. So, ladies and gentlemen, when it comes to subclassing, we have the promises concerns we dealt with the Liskov substitution. Is our subtype making promises that are consistent? The behavior of our subtype making promises consistent with the behavior of the supertype, the guaranteed behaviors of the supertype. But now we have these implementations concerns. And we want to guarantee things even though we can't see a lot of the implementation of the superclass. And we're not going to be notified when it changes. Okay? It's complex because we're going to be overriding some methods of the superclass typically. So we overrode, in this case here, we override get value and set value. And the question is, can we continue to use this other method? Here we overrode add and add all. And we want to continue to be able to use other methods here. And maybe we only want to override add, and maybe that will be enough. And the question is it? So generally we can't see the code for those superclasses. They could change at any point. Someone in the superclass controls the superclass like Oracle's not going to tell us every time they change it. And we need to rely on some details. We need to know what they're calling. So what we're going to be looking at is subclassing contracts here. Okay. I guess I'll make an analogy. Here. So going back to the FedEx analogy, we have FredX. And FredX adheres to the promises made by FedEx as a whole. Maybe it does extra good things. Maybe it guarantees the packages are there by 3 p.m. rather than 5 p.m. Or maybe it allows you to deliver a package as late as 1 p.m. rather than noon. Those are all about the promises. That's all about the subtype. That's the equivalent of subtyping. But now with the implementation, we actually have to deliver on these promises. We've got to make sure our boxes get to the requisite places on the Batmobile or the flights or what have you. And inheritance is basically dealing with a situation where we're using FedEx's systems, ladies and gentlemen. It's not merely we have to adhere to their guarantees. and we can get it to the destination whatever way we want. That we can hire a private plane, or we can send it off with a magnetically powered slingshot or what have you. Instead, now we're going to be using the implementation that FedEx uses. We're going to use their IT systems. We're going to use their planes and their logistics. Then inheritance, we're not just adhering to the promises of that supertype, but we're actually making use of their mechanisms, how it works. And it's like we're using their IT systems. Great, we get their IT systems for our use. We get their planes for our use. We know when the FedEx plane leaves from the Saskatoon airport. Fantastic. But now we're going to be relying on implementation details of them. And we're going to be very sensitive to the fact of that plane schedule. We know, oh, well, the plane leaves from the airport at 2:15, and so, we can let the customers deliver their packages as late as 1 p.m. because we can get a special van over to the airport by 2 o'clock to get it to the plane by 2:15. So here we're relying on implementation details at FedEx. And we need to know all about the detailed operation of their systems. We need to know what to do if their IT systems are down sometimes. We need to know what if the plane has mechanical problems, what our fallback mechanisms are. We get all complicated involved with FedEx's implementation. Okay? We need to know how they work. Not all the details. We don't need to know what the pilot of the plane's name is, that it's Sam, and we're not counting, hopefully, on his name being Sam. But we need to know about certain guarantees that are provided to us as a franchise. These aren't guarantees that FedEx customers know about, but they're guarantees made to us as a franchise. And if we're going to be subclassing, ladies and gentlemen, that's one of the key things we can do. We provide a special interface for subclasses that says, hey, you should know these details about how I work. Not all people who use an instance of my method will need to know those details, but if you're going to subclass me, you need to know these things. So FedEx is presumably going to tell us a bunch of things that your average FedEx customer doesn't need to know because we're a franchise. And similarly, when you go create a subclass, when someone creates a subclass of your class, you've got to tell them extra information. Okay. So here, we have this equivalent of kind of using FedEx's systems, and maybe we override some systems, and some of them we use, and we're going to have to deal with that accordingly. Okay. So we're going to seek to have some sort of modular reasoning about this code reuse. We're going to seek to reuse code without knowing everything about the implementation. And we'd like to be able to adapt their implementation to our needs in a safe way. Okay? And there's going to be a couple different ways to do this. The most basic way, and the way I want you to know the most strongly, is this whole idea of specification. Okay? We've been talking about promises up till now with the Liskov substitution principle. Promises made by a class with respect to those who use instances of that class. So when you have a class and someone's using an instance of that class, they need to know certain guarantees about when they call a method, what's given in return. They may need to know properties like it never declines, it only rises, or that it's always positive, or what happens. They need to know the square root operator returns values within a certain tolerance of the actual value of the square root, and that it only handles numbers greater than or equal to 0. Those are the sort of promises you provide to people who use instances of your class. When I say instances of the class, I mean an instance like this. I'm calling foo on the instance of class B. That's what most of our promises, when we've been talking about promises, that's what they're about, okay? And we've seen how there are certain things like history properties and invariants and method-specific specifications that can be useful for that, okay? And we've seen how we have to adhere to those in the subtype to be consistent with those of the supertype. And fair enough. But guess what, folks? people who create a subclass of your own class need to know more information than that. They need to know more information than your average person who uses an instance of your class. Okay? So let's go back to this example. For someone who uses an instance of a hash set, do they need to know whether add all calls add internally or not? If you're using an instance of hash set, you're calling things like add this thing, or you're calling things like get add count, you're calling add all or whatever. Do you need to? This should really. This is distracting. I want to purge. There we go. So does someone who's using a hash set, do they need to know whether add all calls add? No. No. Whether it calls add or not is immaterial, as long as it does its job as specified. That it takes the union of, what it's passing, and that it's updated to be S, and then the union with whatever elements of this thing. It doesn't matter whether it calls add all or not, as long as it adheres to that promise, that guarantee, right? Does that make sense? Okay. But if you're creating a subclass of hash set, might you want to know if add all calls add? Might you want to have a guarantee about that? Say that again. If you're creating a subclass of add all, such as the one on the right here, might it be useful to have a guarantee in place in writing as to whether or not add all is going to be calling add or not? So that you can make long-term promises about your code, or long-term guarantees about your code that it will work? Might be useful when writing this code on the right to know, for example, that add all does not call add. Would that be useful? Yeah, it could be useful. Are people comfortable with that? Comfortable? You see here, we're assuming that add all does not call add. Because if it called add, we don't need to do this. All we need to do is, we don't even need to override this, right? All we need to override is add. If it, excuse me, excuse me, sorry, excuse you too. If I phrased it the opposite of how I should have. If I had a mental sneeze. So if that was weirdly synchronized. So if add all does not call add, then we don't even need to override. Excuse me. Oh gosh. This is not computing right now. Okay, so if add all did not call add, then that means that add all does need these values in place with plus equal to size, and add should be overridden just like this, in which case this is correct. This is correct if add all does not call add. If add all does call add in the superclass, then what would change? Precisely. You'd remove this add count plus equals c dot size. You wouldn't need this because we'd know that add all up here will be calling this guy. It would add it in. Does that make, and in fact, we could just avoid overriding add all. Does that make sense? Okay, so what I'm saying is, imagine if you could have guarantees, just like you have guarantees like preconditions, postconditions for people who are using instances of a hash set, who are using something that is a hash set and they're calling add all and they're calling that, they want to know what happens. Imagine if there were a further interface that provided guarantees to people subclassing that add all will be calling add, that you can count on that. That would mean that you definitely do not have to override add all here, right? On the other hand, if it said add all does not call add, then you would need these mechanisms in place. Does that make sense? Okay, so the first solution we're going to be talking about focuses on that basic insight. We're going to be providing a separate type of interface. We're going to have separate, distinct subclassing interfaces that reveal some implementation details, like what method relies on what other method, or which data share data with other methods. Okay, and here we're going to have that information be available to those who subclass it. Okay, and if we give too little in the way of guarantees, it may cause subclass implementers to either give up on the idea of subclassing or guess at properties that are not part of our contract and that it could break. Giving too much information limits our flexibility. If we give too much information, we've tied our hands as to how we could evolve this code. Maybe we want to undertake some performance enhancements, but we've already made so many promises that we can't change our data structure. Can you see how that could be an issue? Okay, so let's take a look at this. And I'm going to show you here cases from the actual Java libraries. You'll see exactly this being done. Here's an example of a subclass interface. It's an interface designed for those who are going to be subclassing. It's the lower part of what's shown here. The top is really aimed at particularly at those who are using instances. The bottom provides more details. Okay. Specifically, it notes what this method calls. Remove, it says, it removes elements from the collection using an iterator's remove method. Okay. So here it's noting sort of how it works. You'll notice here's another case, remove range, and you notice it says this method is called by the clear operation on this list and its sublist. Overriding this method to take advantage of the internals could substantially improve the performance. So here there's certain types of information on what calls what that's being provided for those who are thinking about subclassing. Okay, so it says, for example, clear calls this. Okay, you can count on this being called internally by clear. Can people understand why providing these guarantees is useful? Then you can count on it. Then you don't have to worry about your friend and Oracle calling you back. Oh, they changed hash set. Better change your code. Update your customers. No. You don't have to rely on that because you know what's being promised now. Okay? So this is approach one, distinct subclassing interfaces. Okay? You provide extra guarantees like what calls what. Good. Now there's another piece, and this relates to the example that we saw earlier. Here we saw a case where we have a get value and set value, and we provided a pair of them. The question is that enough? One thing I didn't really talk about here is that, ladies and gentlemen, would it make sense? Would it be consistent? Would it be correct, for example, to override set value and not override get value? Generally, that would be bad news. Would it satisfy the Liskov substitution principle in terms of promises? Sure, not a particular problem. But would it be a correct thing? No, it would most certainly be incorrect. So if you were to override get value without overriding set value, for example, overriding set value without overriding get value, and you have a new variable in here, the get value wouldn't be using the new variable. So it kind of makes sense that these get replaced together. And you're going to want to know, do they have to be replaced together with this positive, or is this positive just depend on them? The idea behind the second strategy is related to the first one, in the sense that you say which things have to be replaced together. For example, get value, set value, and int positive have to be replaced as a unit. Why would you need to do that? Well, if you wanted to introduce a new variable which get value and set value depend on, or new data structure, maybe is positive refers to directly to some field in the superclass, and you need to override it as well. So with this strategy, you basically say, okay, which methods do you have to override together? You have to replace them as a unit. Okay. And I'm not going to go into this strategy much. It's been outlined as a viable strategy. The idea is to define different subcomponents of an overall class, and these subcomponents need to be overridden together. Okay. So you override, for example, add element and remove element and elements together. And each of these components, instead of referring directly depending on the implementation of the other components, it just calls methods in the other components. So you can override one component and not have to override the others because they just call the overridden methods. Okay, so that's the second one. I don't expect you to know that in detail. Just be aware that sometimes you have to replace a bunch of things together. Okay? A third strategy. Avoiding self-use of overridable functionality. Okay? So instead of, let's go back to our example here. Here, you notice that foo called bar, but bar could be overridden and was overridden here. And that leads it suddenly to be calling our bar. Okay? Potentially that could cause a problem because our bar might be doing things that are not compatible with what's intended for the behavior of foo. Okay, so the idea here would be instead of doing that, you'd instead have a thing called bar internal, which cannot be overridden. And you have a bar, it calls bar internal, this calls bar internal, but never is foo going to be calling bar. So you could override bar, but you're not going to be able to override bar internal. So foo will always be calling the internal thing. You can override foo, but foo will never be calling the subclass code. It will only be calling its own internal code. So if you want to override it, if you want to change how it works, you can override the whole thing, but you don't have to worry that overriding a different method, like bar, will suddenly change how this method works. Does that make sense? People okay with that? So here, the problem before, ladies and gentlemen, was if we overrode bar, suddenly we're changing how foo works too. If we overrode bar so that it keeps track of these elements, suddenly foo is going to be also adding things to the add count. Here, we would have a bar internal, which would not be overridden, and foo always calls it directly instead of calling the overridden thing. So now we don't have to worry that we've suddenly changed the behavior of foo by overriding bar. Are people comfortable with that? Okay, so the idea is avoid internally depending on things that can be overridden. Okay? Okay, the final or next to final, depending how far we get, approach that I want to talk about today is the issue of, has to do with re-implementation, providing re-implementation rather than error. Okay, so a reminder that inheritance is kind of like committing to use FedEx's systems. It's like saying, okay, not only are we going to adhere to the promises that FedEx makes, promises to our customers, but we're going to actually use FedEx's systems. We're going to inherit all the kind of implementation that FedEx gives us. So we need to know all these details about how FedEx works. Now, you can imagine being a FedEx franchise, a FedEx, where you're not, in fact, depending on FedEx's systems. You know, you have your own fleet, you have your own cars, or you contract out to other planes. You know, you get United to carry your packages, or you get Air Canada to carry them to the neighboring airport, or whatever. We have a completed re-implementation, we still adhere to FedEx's promises, but we use our own resources. We use our own contracting, etc. That's like a complete re-implementation. We can have that with subtyping. And we could adhere to the promises of a super type, but have our own complete implementation of it. In fact, when you implement an interface, that's exactly what happens. We say we have a class which implements an interface, and we implement all the methods of that class, right? Lou? Yeah? Okay. Okay, good. So that's like a complete re-implementation. And in general, this is cleaner. It's not easier necessarily, but it's cleaner. We don't have to worry about all the details of FedEx's systems and what happens if they go off and you know, the schedules of their plane. We can dictate all the conditions, but we may have to do more work. But it's more under our control. Inheritance is a bit less under our control. We're depending on these things about FedEx. Hopefully, we're depending on things like subclass interfaces. Interfaces that guarantee us what calls what. And that would be kind of like FedEx giving us a published schedule and saying these are the times you can count on. Or these are the things you can count on about our IT system. This level of quality of service, guarantees, etc. Okay. So with the fourth approach, the idea is to use a strategy called composition. It's a re-implementation strategy that's particularly easy. And it kind of gives some of the best features of inheritance while also meaning that you're less encumbered, you're less tied up with how FedEx does things, okay? The idea here, and this is key, and this is testable, is that with this approach we'll be using, it provides a way to easily re-implement where we can actually build on an existing implementation, but we don't need to know any more than a customer of FedEx about how FedEx works. We don't need to know any more about the details of the implementation than a user of an instance would need. Okay, it could be, and this stretches the analogy a little bit, but imagine if we were setting up FedEx here in town, and suppose there's not a FedEx outfit over on the west side of town. So we set up a FedEx over there, right? And you know, we're extra accessible to people there. We have you know, very convenient because we're located nearby, and we get people to pay us, you know, as part of that. Maybe even they pay us a bit of a premium because we're located right in their neighborhood. But we have a really efficient way of getting those packages over to a FedEx outfit elsewhere in town and shipping them with them. So we just ship our packages via FedEx. Maybe we even ship them via a per-later courier. We just ship them via another courier service. We get to charge more because we're really convenient. Maybe we have flexible, you know, flexible ways of doing things or what have you. But we're just using another service. And all we need to know, we don't need to know all the details about FedEx's IT systems work or their schedule of their planes. We're just another customer as far as how we're using them. Okay, so let's talk about this. So you remember this hash set with add all and add, right? And you recall this risky inheritance here. And a lot of the issue was, does add all call our method add or not, call the method add and by extension our method add or not? Okay, this is an alternative. Okay, so ladies and gentlemen, here we have an instrumented set. It implements the set interface, and we provide our own implementation of all the methods. But that implementation is particularly simple. Can anyone see what's going on here? What's going on? Are we having to, like for the clear operation, are we having to write a lot of code and loops? Or for the remove all, why aren't we seeing lots of code and loops and complicated data structures? What's going on? What is this code using? and as an instance of it. As an instance. It's as if we have an instance of perlated that we can use. Now, we've got FredX or FredX, we have great guarantees, and then we take your package and later, getting the perlated deadline, and so we go out and we drive it on our bat cycle over to perlated courier and drop it off, and it gets shipped out there. Here, we've got an instance of set that we're using. Now, note, folks, that we have get add count here. This is our instrumented hash set. Ladies and gentlemen, this is what I want you to think about. And I'd ask you, ladies and gentlemen, to think hard about it. Does this code have the promises, or have the problems that we saw with this code? Does it have problems in terms of knowing, of being dependent on things that aren't under our control? Things that are implemented by someone else? Do we have to worry, for example, about how the add all of this set here is implemented? No, we don't. We're just using it as if we're using an instance of this thing, of set. And here we're keeping track of add count and returning add count. Why is it, ladies and gentlemen, that we don't have to worry about, for example, does this add all call add? Why is it we don't have to worry about that here? It will call its own add. We're not creating a subclass of add where we're overriding, for example, add. Instead, we're just using it as an instance. It's going to call its own add. If it calls its add, it calls its add. If it doesn't call its add, it doesn't call its add. It just gets the job done. We can have our own add. We just add, to add count here. We add this thing in, add all, adds it in here. We don't have to worry that add all is going to somehow call our add because it doesn't know about our add. Does that make sense? So ladies and gentlemen, this is a wrapper class. This is a class that takes an instance here of any set. This is like Perlator. It's like FedEx or it's like UPS or whatever. Some other service that we make use of. We're just a client of that service. We're just a customer of that service. Just using it as an instance. And we can provide all the added functionality we want here. And we don't have to worry we're breaking this thing. Is that clear? We don't have to worry we're breaking it, but we can still make use of it. It's not like we have to go and implement separately in gory detail all these methods. It's not like we have to go and create a lot of code for them because we can always delegate. We're just delegating to this instance passed in of set. We're just calling off to its things. So we're getting the job done with a minimal mechanism. We don't have to write much code. It's a little bit ugly, but it's totally straightforward. And we don't have to worry we've broken it. Is that clear? Folks, is that clear? Yeah? We don't have to worry we've broken this set S because it doesn't know about our add. We call it to add all. It does whatever it does, however it does it. We don't have to get involved. Whatever FedEx's schedule is for shipping planes out of here, we don't have to know. We're just a customer of them now. Okay? Now we're a FedEx franchise. We have to make the guarantees, and we're implementing the set interface, but we're doing it atop of another set that's already implemented, and then we're extending it a little bit with get add count. Can you see why this is safer? Can you see why it's cleaner to a degree? At least from one perspective, you could view it as cleaner. You're not all involved with the internals of what calls what, etc. It's a little bit messy like this. I would argue within your professional lifetimes, this will be trivial. You'll just be able to say, create a wrapper class of this thing. Automatically, these things get created, and you just override the ones you're interested in. Boom, done. Cleaner than that. So here, we have a common subtype, in this case set, and we can just pass this instrumented set around as if it's a set and get all the benefits of polymorphism get the benefits of polymorphism, and do it in a cleaner way where we're not tied up with how this is implemented and how that might change in the future. Does that make sense? Okay. Good. Okay. Think we will we'll stop that. Yeah, stop that there. So I guess, well, I'll make one final point. The final thing, just to sort of close off the set of all things. The best thing to do, where is it? This. The safest way to deal with subclassing your classes is to prevent it. I'm not saying you should do this always, but if you don't want to create a subclass, if you haven't designed it and planned for it, if you haven't documented what calls what, for example, and really thought through what things are overridable, what things are not, is this safe? You can make it impossible to subclass. And this is what's recommended. If you go to the Effective Java Books, Block recommends it for many, many cases for these reasons, because it gets messy. When you want to create a class to be subclassed, you have extra responsibilities in terms of documentation. So if you don't want to do that, declare a class as final. This is a final class. It cannot be subclassed. Alternatively, make the constructors private or package private, and use the static factory method associated with the class. So it's a static method to create instances of the class. Okay, no one can override it then. The alternative is use this composition or wrapper classes that we just discussed. Wrap up things, just delegate to them, and add the fit functionality on top, and it will be straightforward. You can avoid the hazards, the problems, the risks associated with this sort of system. Okay. Okay. So that's all for today. Excuse me. That's all for this session. It is not all for today. I'll be back in about an hour and a half, right, to see your presentations. Thanks very much.